Welcome to the 27th lecture of combinatorics. In this class we will look at non-homogeneous recurrence relations and propose some methods to solve it. It is not that these methods will work always, but this is the way one can try to solve it. So, in the last class we had discussed this Tower of Hanoi puzzle. We saw that we can formulate, so the puzzle will give rise to a recurrence relation Hn equal to 2 into Hn minus 1 plus 1, right. So, the question was how to solve this recurrence relation. We saw how to unroll this recurrence relation, that means Hn equal to 2 into Hn minus 1, that is equal to 2 times 2 of Hn minus 2 plus 1, and that like that we got a sequence of numbers which we added in the end, and it was like 1 plus 2 plus 2 square plus 2 cube plus like that, and we got in the end the answer 2 to the power n minus 1, right. So, now the intention here is to look at a different procedure, right, which probably can be called a little more general, that we can try to apply it whenever we have a situation like this, right. So, this is there are 3 steps. So, first step, we find the general solution of the corresponding homogeneous relation. So, what do I mean by that? For instance, in this Tower of Hanoi case, we have Hn equal to 2 into Hn minus 1 plus 1. So, what is the homogeneous part here? So, we know that the homogeneous part is this, because this is that Bn, remember, right. Bn, when we formulated our kth order recurrence relation as Hn equal to A1 into Hn minus 1 plus A2 into Hn minus 2 plus finally Ak into Hn minus k plus a Bn. This is what we wrote, right, and we told this when this Bn is 0, then it is a homogeneous recurrence relation of order k, and linear, of course, linear homogeneous recurrence relation of order k, that is what it. But then suppose Bn is not equal to 0, then we say that it is non-homogeneous, right. Here this is a non-homogeneous recurrence relation, because here Hn equal to 2 into Hn minus 1, here A1 is equal to 2 and Hn minus 1, and there is nothing more, because k equal to 1 here is a first order recurrence relation, and then this plus 1 corresponds to this Bn here, right. So, now there are 2 parts to it. So, there is a homogeneous part to it. The homogeneous part is Hn equal to 2 into Hn minus 1, which means we just discarded the other part, this plus Bn part, plus Bn, in which case here it is 1. So, this we just remove, and this is called the homogeneous part of the recurrence relation. So, this we can easily solve, because this is Hn minus 2 Hn minus 1 is equal to 0, and the characteristic equation is x minus 2 is equal to 0, and that implies x equal to 2, right, is the solution of the characteristic equation. And then the general solution for the homogeneous part is Hn equal to some constant c times 2 to the power n. Remember, 2 was the solution of the characteristic equation, right, this we remember. Now, what we do is, so remember we have the initial conditions, so H0 equal to 0 and H1 equal to 1 for the Tower of Hanoi. There are 0 disks, there is 0 moves required, there is just one disk on the first peg, we just need one move, right. These are the initial condition. We have to fit this thing, and not only that, this only fits the homogeneous part, The actual recurrence relation is not Hn equal to 2 into Hn minus 1, but rather Hn equal to 2 into Hn minus 1 plus 1. So, what we do is we find a particular solution of this thing, right. So, we will go back to the steps. The first part was find the general solution of the corresponding homogeneous relation. Then we find a particular solution of the non-homogeneous relation. Non-homogeneous relation means this full relation, right. What is this particular solution? So, what we do is we will find a solution which will work for some initial condition, some particular value of H0, right. For instance, what I do is I will substitute. So, I will see whether if I take some constant it will work or not. For instance, take a number say D, right, or we can say a number K, let us say K being a constant, right. So, Hn, some solution like Hn equal to K is what I am saying. That means is for some number K, can this sequence K this sequence satisfy Hn equal to 2 times Hn minus 1 plus 1. This is the question, right. So, let us try it. So, Hn has to be equal to K, that is 2 into Hn minus 1, that is again has to be K because Hn minus 1 and Hn both are K, right. All of these Hi's are K's plus 1. So, is it possible to get some solution for this thing? This of course, if you cancel K here, you get 0 here, and this becomes 1 K, and then that means K is equal to minus 1. So, if you take K equal to minus 1, it will indeed be true. That means this sequence, consider the sequence minus 1 minus 1 minus 1 minus 1 minus 1 so on, right. So, it is true that if you add 2 times minus 1 plus 1, that is indeed another minus 1, right. 2 into minus 1 plus 1 is minus 1. So, it is satisfying that recurrence relation Hn equal to 2 times Hn minus 1 plus 1, right. So, this is a particular solution, right. You could find this particular solution. The good thing now is why did we find a particular solution like this? See, this particular solution will not be a valid solution for us. Why? Because this indeed satisfies our recurrence relation, but it does not satisfy our initial condition, namely H0 equal to 0, H1 equal to 1. These things are not satisfied, right. So, okay, we need only one initial condition. So, H0 is equal to, we can start with say H1 equal to 1, for instance. That is more clearer that this is what we are talking about, because when one disk is there, so we need one move, right. But because these are all minus 1s, then H1 is not equal to 1 here. So, this is not a correct solution for us, but then we can use this particular solution and the general solution to create a lot more solutions. How? Combine the general solution and the particular solution and determine the values of the constants arising in the general solution, so that the combined solution satisfies the initial conditions. This is what we should do. This is the third step. So, again I am saying, if Hn equal to C times 2 raised to n will satisfy what? This will satisfy this relation Hn equal to 2 times Hn minus 1, right. Now, this sequence minus 1, right, Hn equal to minus 1, Hn equal to minus 1 will satisfy this entire relation Hn equal to 2 into Hn minus 1 plus 1. So, what is not satisfied is the initial condition, that means H1 equal to 1. This is what what is not satisfied. So, to satisfy this also, right, what we should do is we should create another solution, namely we will add up these two. So, for instance, Hn equal to C times 2 raised to n plus 1, will this be a valid solution for the recurrence relation? It is indeed, because you know, if you substitute C h n equal to C into 2 raised to n plus 1, sorry, n minus 1, sorry, this h n minus 1. So, what I did is I added these two things together, right. Then what happens is, so if we consider this part h n minus 2 h n minus 1 minus 1 equal to 0, if this is the way we write that recurrence relation, and if we substitute this to here, C 2 raised to n minus 2 times C 2 raised to n minus 1, that will become 0, because you know this homogeneous part of the recurrence relation, that means h n equal to 2 h n minus 1 or h n minus 2 times h n minus 1 is indeed equal to 0, is satisfied by C times 2 raised to n for any C. So, it does not have any effect, that is what this part does not have any effect on it, it simply disappears from this itself. But on the rest is minus 1, if you put minus 1 for h n and here also minus 1, we will get minus 1 minus 2 another minus 1, alright. So, what happens is this minus 1 and minus 1, that will become minus 2, here minus 2 times minus 1 will become plus 2. So, that is indeed becoming 0, right. That is clear, because when I put h n equal to minus 1, this entire thing is anyway satisfied. The extra C times 2 raised to n has no effect on this, because h n minus 2 h n minus 1 itself will nullify the effect of that, because if you substitute C 2 raised to n here and 2 into C 2 raised to n minus 1 here, that gets that becomes 0. That is what the meaning of this h n equal to C times 2 raised to n is the solution of h n equal to 2 into h n minus 1. So, we understand that since h n equal to C times 2 raised to n is a solution of the homogeneous part, that h n equal to 2 into h n minus 1, and h n equal to minus 1 is a particular solution for this one, h n equal to 2 times h n minus 1 plus 1. So, indeed h n equal to C times 2 raised to n minus 1 is a solution for this recurrence relation. So, this part, right. So, now we have a C there is a constant here which we can decide the way we want, that means C times 2 raised to n minus 1. Suppose if you put n equal to 1, so that is then what will happen, this will become C times 2 minus 1. So, but you know when n equal to 1, we need the answer to be h 1 equal to 1, right. So, what is this, C times 2 equal to 2, right, that means C equal to 1, right. C equal to 1 will satisfy our initial condition, which means C times 2 raised to n minus 1 is a solution, is what we told. Put C equal to 1, that means 2 raised to n minus 1 is indeed the solution for our recurrence relation, which satisfy our initial condition, right. So, this is exactly what we got in the other way also. So, we elaborately described it to explain the methodology. There are 3 steps in it. First, we consider only the homogeneous part and solve the homogeneous part first by the techniques we have already learnt for solving the homogeneous linear recurrence relation with the constant coefficients. Then we get a particular solution for the entire non-homogeneous recurrence relation, right. It will just work, it will work for some initial values, but not for every possible initial values. So, in particular our the initial value given to our problem may not be satisfied by this particular solution. Now, what we do is we combined the general solution for the homogeneous part plus with the particular solution for the non-homogeneous recurrence relation we have, and that is indeed a solution for the non-homogeneous recurrence relation given to us, right. But then the good thing is there is a constant available there which we can manipulate, which we can fine tune to meet our requirement. What is the requirement? We have to meet the initial condition. We substitute the n equal to whatever, maybe 0, 1, whatever, and then we get an equation involving C, and we solve for it. That is what we do. We will take yet another example and see what happens. If Bn is a before getting further, we will just mention that here of course there are two parts. One is first find the general solution for the homogeneous part. There you have to solve the characteristic equation. Of course we can easily find the characteristic equation. The difficult part is to get the solutions for the characteristic equations, which may not be so easy because we do not have techniques to solve any polynomial equation. So for instance, if it is a higher degree polynomial, we may not be able to do it so easily. So that is the difficulty in it, in using this method. But somehow we can find the roots of the polynomial. Then so we can get by our earlier methods some particular solution for this thing. We have given both general solutions for this thing. General solutions in the case of all distinct roots, and also when the roots are repeating, we have given solutions for this thing. But the next part is to find the particular solution, right? Particular solution, how will you go about finding the particular solution? In the Tower of Hanoi case, what we did is we just substituted, we saw whether a constant would work or not. Will sequence like k, I mean unchanging values, will it fit the given recurrence relation? Definitely it need not fit in all cases, right. So here we need, sometimes we may need some different kind of substitutions also. So here there is a list what kind of particular solutions we may try. For instance, if your Bn is indeed a constant, like in our previous example it was 1 there, then we can try a constant like this if it may work. So if Bn is of the form dn plus e, some linear in n, right, d times n plus e, then we can use Hn equal to Rn plus n, Rn plus s. So see, it is not that always if you substitute this thing this will always work, but this is the thing to try. Then similarly, if Bn is equal to f times n square plus dn plus e, then we can try Hn equal to R times n square plus Sn plus d. So where R, S, T, etc. are some constants, right, f, d, e, all of them are constants here. If b is an exponential, that means like b equal to d raised to n for some constant d, then what we do is try Hn equal to p times d raised to n for some other constant p, right. So these are some guidelines for finding the particular solution. Now you see, once you can get a particular solution, then see what happens is you can sum up the general solution for the homogeneous part and the particular solution, and then solve for the constant so that the initial conditions are met. That is what we should do. So now we will get some experience by looking at some problems. For instance, look at this problem, Hn equal to 3 times Hn minus 1 minus 4n, for n greater than or equal to 1, and for H0 you have 2. Initial condition is H0 equal to 2. Hn equal to 3 times Hn minus 1 minus 4n. Here you can see that it is a non-homogeneous recurrence relation which is linear and of order 1, and non-homogeneous because Bn is not 0 here, Bn equal to minus 4n here, right. So now this is the recurrence relation, Hn equal to 3 times Hn minus 1 minus 4n, right. We have H0 equal to 2 for our initial condition. The first step is find the general solution of the homogeneous part. Homogeneous part is Hn equal to 3 times Hn minus 1. Clearly the characteristic equation here is x minus 3 equal to 0, which means x equal to 3. So general solution for this one is Hn equal to some constant c times 3 to the power n. So for this thing you can substitute c times 3n, whichever is the constant, c times 3n, it will work. You can see that, right? C times 3n, if I 3n minus you put here, c times 3n is coming, and that is exactly the value for HM, right? So the next step is to find a particular solution for this one, particular solution for this one, 3 into Hn minus 1 minus 4n. So now we are saying that this is of the second type, right? So second type means we will go for the chart here dn plus c, then rn plus s is what we should try. So if this is minus 4n plus 0, so this is of this form, second, right, category. So we will try Hn equal to Rn plus s for the particular solution. Hn equal to, this is what we will try, Hn equal to Rn plus s. Here this R and S both are constants, right? See whether it will work or not. So that means you substitute for Hn. So what we get is Rn plus s equal to 3 times R into here n minus 1 plus s minus 4 into n. So now we have to simplify. So this is 3Rn. We get here 3 times Rn minus 3R plus 3s minus 4n here. Right now we can collect the terms involving n together. That is 3R minus 4. This is equal to Rn plus s equal to 3R minus 4 into n plus 3R minus 4 into n plus 3s minus 3R. 3s minus 3R, right? This is what you see. Now we can compare the coefficients of n. If here the coefficient of n is R here, so R has to be equal to the coefficient of n here, namely 3R minus 4, right? So which would imply that 2R is equal to 4 is equal to, which will imply that R equal to 2, R equal to 2. Now we can compare the constant terms. Here it is s equal to 3s minus 3R is the constant term here. So that would mean 2s equal to 3R, that is 3 into 2, 6. So what does it mean? S equal to s equal to 3. We get R equal to 2 and s equal to 3. So our particular solution is 2n plus 3, 2n plus 3. So we can try it out. See, if we substitute 2n plus 3 in our recurrence relation, Hn equal to 3 times Hn minus 1 plus, sorry, minus 4n, it should indeed work is what it says, right? It will work. So if you want to try it, so you can just check it. 2n plus 3 equal to 3 into 2n plus 3, that is 6n plus 9. Sorry, this is Hn minus 1. So it will become 3 into 2 into n minus 1 plus 3 minus 4n. So here we have 6n, here we have minus 2, minus 6 plus 9, that is plus 3, right, and minus 4n. So which will make it 2n plus 3 as we want. This and this are same. I just verified whether it is this particular solution is indeed 1, but only one problem here. So if 2n plus 1 is the solution, this will not meet our initial condition. For instance, we wanted h0 equal to 2, right? That's what we mentioned before. h0 equal to 2. h0 equal to 2 is what we wanted. But in this case, if we put n equal to 0, what will happen is 2 into 0 plus 3, that will be 0, 3, h0 will be 3 here, right, but we want h0 equal to 2. What will we do? So, this particular solution is indeed valid for the recurrence relation, but it is not satisfying the initial condition, and we do not have any thing to tune, because there is no constant which we can select according to our requirement, right. So, what we do is we will combine the particular solution 2n plus 3 with the general solution of the homogeneous part, right, which was C times 3n, right. This is indeed going to be a solution for your, so if I take hn equal to this will indeed satisfy hn equal to 3 into hn minus 1 plus minus 4n, right. Why? Because you know this part is a solution for this thing, and when I substitute this, the contribution due to this will be cancelled here, right. So, here and here the same contribution, and now we only have to worry about whether this will balance both sides. I mean, when I give this thing here and this thing, and this thing is I mean, for instance 2n plus 3 part is given to put n equal to n minus 1 here, substitute. So, will it satisfy it or not? That is all we have to worry, and we have already seen that this solution hn equal to 2n plus 3 will satisfy this thing. The contribution from this thing is anyway balanced due to the fact that this was a solution for this hn equal to 3 into hn minus 1, the homogeneous part, right. So, therefore, this is indeed a solution for this thing. So, what is good about this new solution? The good thing about this new solution is that there is a C here, and this C we can choose. It's irrespective of whichever C we put, this relation will be satisfied, because that does not depend on this C, right. But on the other hand, that tuning this C, fixing the C at a correct value will help us to get our initial condition satisfied. What is the initial condition? h0 equal to 2. Now, you try putting n equal to 0, we get, this will go away, we get 3 plus C, 3 plus C equal to, so that means 3 plus C has to be 2 is what is saying. So, we can decide our C to be minus 1, right. If you decide our C to be minus 1, it will work. That means, here we have to put minus 2n plus 3 minus 3n, that is all, right. So, we could find the value of C, so that this not only satisfy the recurrence relation, but it also satisfy the initial condition, right. Right, h0 equal to 2 here. So, that is the idea. So, again recall that we have how we have gone through 3 steps, and then how we got the solution in the end by solving for the constancy, right. Now, we will try one more example. Let hn equal to 2 into hn minus plus 3 raised to n, right. This is the this is a slightly different example to show that this may not always easily work. Hn equal to 2 into hn minus 1 plus, what was that, 3 raised to n, right, 3 raised to n, sorry, this I do not know, let us see what is this. So, n greater than or equal to 1 only it works, h0 equal to 2, we have h0 equal to 2, this is the initial condition, because we can only, it is a first order relation. So, we have this recurrence relation working starting from n equal to 1 onwards, n equal to 0 we have to give a special the value, initial value, right. Now, to solve this thing, the first step as usual, we separate out the homogeneous part hn equal to 2 into hn minus 1, and its characteristic equation, that is x minus 2 equal to 0. The solution of the characteristic equation is x equal to 2, right. Now, if the solution of the characteristic equation is x equal to 2, then we know that the general solution is hn equal to 2 into c into 2 raised to n. This is for the homogeneous part. Now we have to find a particular solution for the entire non-homogeneous equation, namely hn equal to 2 into hn minus 1 plus 3 raised to n. How will you find the solution, particular solution for this thing? So we look at our chart. So when we look at our chart, we see that if Bn is an exponential, like Bn is equal to d to the power n form, then we can try hn equal to something like p into d raised to n, right? P into d raised to n, right? So here 3 raised to n. So we will try hn equal to some p times 3 raised to n, right? This is what we will try. So that means we substitute it, p into 3 raised to n equal to 2 into p into 3 raised to n minus 1 plus 3 raised to n, right? Now we can cancel off this 3 raised to n minus 1 from all here. We get 3 here, 3 here, right? So that means 3p equal to 6p plus 1 is what we will get. Am I right? So we put hn equal to p into 3 raised to n. So 2 into p into 3 raised to n minus 1 we put, right? Because hn minus 1 only we consider, and this is 3 raised to n. Of course, we can cancel off 3 raised to n from everywhere. So, but let us look whether I am taking this 2 only. So we get, so from this thing what do we get? 3p plus 1 equal to 0 is what? 3p plus 1 equal to 0 is what we are getting. So we get p equal to minus 1 by 3, right? Minus 1 by 3. So now of course this will minus 1 by 3. So what will be hn then? Hn equal to p times 3 raised to n, that is minus 1 by 3 into 3 raised to n, that is minus 3 raised to n minus 1. This will be the particular solution. So if you want to check whether it is working, yeah, so minus 3 raised to n minus 2 here, right? So and then minus 3 raised to n minus 1. Yeah, this is 3 times 3 raised to, sorry, 2 times 3 raised to n minus 1. This is 3 times 3 raised to n minus 1. That is 1 times 3 raised to n minus 1, minus will stay here, and then so once again, so I don't know. So we wanted to find a particular solution. I put hn equal to 2 times hn minus 1 plus 3 raised to n. So we get p times 3 raised to n equal to 2 times p into 3 raised to n minus 1 plus 3 raised to n. Right now, okay, this is not 1, this is 3 plus 3, because here I cancel 3 raised to n minus 1, here 3 is remaining, here 2p is remaining. Okay, this is 2p is remaining, and then here it is 3p. So we can see that p equal to 3. So this was wrong, p equal to 3 is what is coming, right? So p equal to 3. So this will be 3 raised to hn equal to 3 raised to n plus 1. Now we will check whether it is working out on this thing, that hn equal to 2 times hn minus 1 plus 3n, right? Yeah, because this is 3 raised to n plus 1. When I substitute hn equal to 3 raised to n plus 1, this will be hn minus 1 will be 3 raised to n, 2 into 3 raised to n plus 3 raised to n is 3 into 3 raised to n, that is 3 raised to n plus 1. So, it is working out. So, that is indeed a particular solution for the given homogeneous non-homogeneous recurrence relation, this one. So, now we will combine this particular solution. See again, note that this particular solution it is working fine with the recurrence relation, but the initial condition will not be met, because I will go back to the initial condition is again h0 is equal to 2. So, that is not met here, right, because we see 3 raised to n minus 1, if you put 0, that 3 raised to n plus 1 is put n equal to 0. So, that will only give 3 raised to 1 equal to 3, that is not 2, right. We want for n equal to 0, we want hn to be 2, h0 is equal to 2, we are given that. So, but if you take this particular solution alone, it is not true, right, it is giving actually 3. So, how will we find a solution which will satisfy our initial condition also? So, what we do is we combine the general solution for the homogeneous part, namely c times 3 raised to n, c times 3 raised to n, or c times 2 raised to n, this was the homogeneous part solution, c times 2 raised to n, and our particular solution 3 raised to n plus 1, right, and try putting n equal to 0, we get h0 equal to 2. So, putting n equal to 0, we get c plus 3 equal to 2, that is c equal to minus 1, c equal to minus 1. That means our solution will become hn equal to minus 2 raised to n plus 3 raised to n plus 1, right. So, indeed this will satisfy the recurrence relation. Now, if you put n equal to 0, what you get is here 3, this is 3 and this is minus 1, right, n equal to 0, 3 minus 1 is equal to 2, as we want, h0 is indeed 2 here, right. So, it is satisfying our initial condition also. So, this was our last. Now, we will look at our last example, namely, so it is a slight modification, hn equal to 2 into hn minus 1 plus 3 raised to n is what we looked. Now, we will look now hn equal to 3 times hn minus 1 plus 3 raised to n, hn equal to 3 times hn minus 1 plus 3 raised to n. So, this is only valid for n greater than or equal to 1. So, we need to give the initial condition h0, that is again 2, right. So, now particular solution, first we take the homogeneous part, that means hn equal to 3 into hn minus 1. We write the characteristic equation x minus 3 equal to 0, solve it, that means x equal to 3 here. So, now we infer that the general solution for this thing is hn equal to c times 3 raised to n for any constant c, right, this is the general solution. Now, we look for a particular solution for this, hn equal to 3 into hn minus 1 plus 3 raised to n, right. So, what we can do, we go back to the chart. So, if you recall the chart would say, because it is an exponential bn equal to d raised to n, then try p times d raised to n, right, try p times d raised to n is what it will say. So, hn equal to p times 3 raised to n is what it proposes to try, but we have tried it earlier for the hn equal to 2 into hn minus 1 plus 3 raised to n plus. Let us try it again. So, this is p times 3 raised to n is equal to 3 times p into 3 raised to n minus 1 plus 3 raised to n, right. Now, this is what? This is again, this is p into 3 raised to n plus 3 raised to n. We cancelling this, we get 3 raised to n equal to 0, right. This is what it keys, which is not true. Or yeah, we are getting for when you cancel 3 raised to n everywhere. So, p equal to p plus 1 is what we are getting, p equal to p plus 1 is what we are getting. So, which is absurd, right. So, we cannot solve, we cannot get such a value of p. So, that means h n equal to p times 3 raised to n. If you take h n equal to p times 3 raised to n, there is not going to be a particular solution for this non-homogeneous recurrence relation of that form. So, what we do, we then change the pattern of the particular solution a little bit. We will try h n equal to p times n into 3 raised to n, right, just for a, I mean, it's a slight change we give, and then we again try that. So, now h n equal to 3 times h n minus 1 plus 3 raised to n will become p into n into 3 raised to n equal to 3 into p into n minus 1 into 3 raised to n minus 1 plus 3 raised to n, right. Now, this is, we can cancel off all the 3 raised to n's here, right. So, that means p n equal to p n minus p plus 1, this is what we will get. So, p n also goes away. So, we get p equal to 1, right. So, we get a solution for p now. So, we get a particular solution p, the particular solution h n equal to p times n into 3 raised to n, that is p being 1 as n into 3 raised to n, this is the solution, right. So, we can try it out here, you will see that is correct, right, because this is 3 n into 3 raised to n, this is 3 into n minus 1 into 3 raised to n minus 1. So, n into 3 raised to n equal to 3 into n minus 1 into 3 raised to n minus 1 plus 3 raised to n, right. So, this is n into 3 raised to n here minus 3 raised to n plus 3 raised to n. So, here n equal to 3 raised to n, this is true, right, this is indeed correct. So, n into 3 raised to n is indeed a particular solution. Again, as we were always seeing, if you try whether the initial condition is met, it is not met, because if you put n equal to 0, this will become 0, right. So, n into 3 raised to n is indeed 0. So, but we want h 0 equal to 2. So, how will it happen now? So, what we do is we combine the initial combine the general solution c into 3 raised to n. This general solution was for the homogeneous part alone, h n equal to 3 times h n minus 1. This is combined with the particular solution that we obtained for the non-homogeneous recurrence relation, that full recurrence relation, namely n into 3 raised to n, right. So, now we want when we will check when n equal to 0 what happens. So, n equal to 0, this will be c plus c, right, this will be simply c because this will go away, this is c, and this has to be equal to 2. So, therefore, we select c equal to 2 and substitute here. So, 2 into 3 raised to n plus n into 3 raised to n, that is n plus 2 into 3 raised to n is indeed a solution for the given recurrence relation, which satisfies the initial condition also. That is what we get, because if you put n equal to 0, you will get 2 here, and indeed by our the construction of this solution, we know that it satisfies the recurrence relation. So, now going back to the right. So, this is our last example. So, of course, this whatever we have done are some examples, but it illustrates a general strategy to attack these kind of problems, but success is not guaranteed always. Success is not guaranteed always. Sometimes it may fail, in which case you may have to do some slight adjustments and go forward, or sometimes it may not work out. So, we have taken some examples of to illustrate all those points, right. So, now what we do is we will look at the next topic, namely generating functions. So, what are these generating functions? So, consider a sequence H0, H1, H2, H3 like this. Now, the generating function corresponding to this sequence is given by this power series H1 raised to x1 plus H2 into x raised to 2 plus H3 into x cube plus so on. This is the power series. So, let us say you write it as g of x, right. This g of x is the generating function of this sequence Hn. So, now it is not always necessary that we should have all these, I mean Hi's to be an infinite sequence. Suppose in some cases it may be just H0, H1, H2, and after some time all of them may become 0, right. So, this is indeed an infinite sequence in that sense, but otherwise only the relevant non-zero terms are come only in the first n terms, a finite number of terms, right. That is also possible. So, we will look at some examples. So, we will start with the most familiar example, namely let H0 equal to m choose 0, let H1 equal to m choose 1, second number, third number be m choose 2, and fourth number be m choose 3, and so on. So, Hm equal to m choose m, and Hm plus 1 onwards it is all 0, right. So, now Hm plus 1 onwards it is 0 0 0 0. So, this is a sequence. What is the generating function of it? The generating function of this is given by m choose 0 plus, because we are writing this as H0 of case. So, m choose 1 into x raised to 1 plus m choose 2 into x square plus m choose 3 into x cube plus like that until you reach m choose m into x raised to m. So, the rest of the terms are all 0. So, we can discard them. So, this corresponds to H0, this is H1, this is H2, and until this is Hm. Okay. Now, what is this? This we know already, that is this is 1 plus x whole power m. So, the generating function g of x for the given sequence m choose 0, m choose 1 to m choose m is 1 plus x raised to m, right. Now, so that is probably the most familiar generating function for us. So, now we will look at some infinite series. This is 1 plus 1 plus, so this infinite series. So, means all this is H0, so H0, H1, H2, H3, so like that. So, 1 1 1 1 1 1, right. So, the generating function is 1 plus x plus, see 1 into x, okay, 1 into x square plus 1 into x cube plus this infinite series. So, this is equal to 1 by 1 minus x. So, this is the generating function for it. So, if you want to convince yourself, so you can recall that, for suppose this 1 1 1 1, suppose there are n ones and later all are zeros, then what will be the corresponding generating function? It will be like this, x plus x raised to n, right. sorry, n terms means including 0 up to n plus 1th term. That means this corresponds to h0, this is h1, this is h2. So we write up to hn. So we have 1 plus x plus up to hn. So this we know is 1 minus x raised to n plus 1 by 1 minus x, right. So so for instance, if you can try multiplying 1 minus x into 1 plus x raised to n, right. This will be indeed 1 minus x raised to n plus 1, because when you multiply by 1 you will get this, and when you multiply by minus x, so you will get a minus x here, minus x square from here, and finally minus x raised to n plus 1. So all the terms except the first one, and from the first one and the last x raised n will be. So for instance, if you want to see this, it is like x raised to, when I multiply by 1 here, this entire term will come x raised to n minus when I multiply by x, we will get x plus x square plus x raised to n plus x raised to n plus 1 will come, right. So these terms will go away. So you get 1 from here minus x raised to n plus 1 here. This is what we will get, right. So that is why this sequence has generating function 1 minus x raised to n plus 1 by 1 minus x. Now you can see that the same technique will tell us, for instance, if this was an infinite sequence, it is not ending at x raised to n. So it is 1 plus x square plus x cube plus, the same argument would tell us that that is equal to 1, because there is no, in the end what happens is this x raised to n plus 1, that is tending to 0. So we can say that 1 minus x into 1 plus x square plus is equal to 1, right. So that means your 1 plus x plus this sequence is equal to 1 by 1 minus x. The only thing we have to worry about is, so this, when we argue this thing, we have to worry about whether this converges or not. So yeah, it will converge for when x is less than 1. So yeah, in all of our discussions we will not worry too much about this part, convergence, because we will be worried more about the coefficients of the powers of x which is coming here, and we will not be discussing the issue of convergence all the time. So therefore yeah, and we will be dealing with familiar forms where, so for some ranges it indeed converges, for which range it converges it will not be relevant to our discussion, right. We will not be trying to sum up the series anyway. So now the next one, so we will, yeah, this, now that we have seen this one, yeah, so we can also cook up some other sequences. I mean, see, from this thing 1 minus, this is 1 plus x square plus this thing, that is this g of x equal to 1 by 1 minus x is the generating function of the sequence 1 1 1 1 1 etc. Now what we can see is that this part, if you differentiate, you will get 0 plus 1 plus 2x plus 3 x square plus and so on, right. So if you differentiate this portion, we will get minus 1 by x square, sorry, whole square, because this is minus 1 by x square and there is a minus x here, so therefore it is plus 1 by x square. But then here we have 0 that we can anyway remove, 1 plus 2x plus 3x square. The only thing is here 2 is the coefficient of x, right. Either we can say this is the generating function of the sequence 1, 2, 3 and so on. So h0 is equal to 1, h1 equal to 2 and h2 is equal to 3 and so on. That means the sequence hn equal to n plus 1, that is what it is. So so this is the generating function 1 by 1 minus x whole square is the generating function of such a sequence. Or we can, what we can do is we can multiply here this side by an x, this side by an x, right. So x into 1 minus x whole square, that will introduce an x everywhere here. So like this, right. That means this exponent which is coming at x to the power what, that will be the same as the coefficient of that term, right, coefficient in that term. So therefore, so just that we are starting with x, not with a constant term. So therefore we can say that we can put the constant term as 0, the first term as 0, 0 plus x plus 2x square plus 3x cube and so on. So we see that x by 1 minus x whole square is the generating function of the sequence 0, 1, 2, 3 and so on, that is hn equal to n, the sequence hn equal to n, right. So now yeah, so before getting into the next one, what we can mention is, so if you want to generate a so it's a good exercise to try to find the generating function for 0, 1, 2 square, 3 square, this sequence 4 square, 5 square and so on. So how do we do that? Because we know that our x by 1 minus x whole square is the generating function for the sequence 0 plus, right, 0, 1, 2 and so on, that is x plus 2x square plus, this is the sequence it is representing, right, this one. So you can see that if you differentiate it further, d by dx of this one, this gx, if I take, right, this being gx, then what will happen here is this will be 1, this will be 2 square x plus 3 square x square and so on. So we see the term which we want, terms which we want here, but just that 2 square is the coefficient of x. So what we can do is we can multiply by what, so x here, so this will be x. So if you multiply x by x here, then we will get x plus 2 square x square plus 3 square x cube and so on here. So now this function will be the generating function of this. That means this is the generating function corresponding to 0, 1, 2 square, 3 square, etc. And if you consider this function, that will correspond to the thing we will discuss in the next class.